This is Deya Chatterjee, MS 17057. This presentation has been made for fulfilling the requirements of the course IDC 452 Seminar Delivery for Physics Majors. Today, I'll be presenting on the topic Quark-Gluon plasma, a new state of matter. So, what is QGP? In the standard model of particle physics, quarks and gluons are two fundamental particles and form the building blocks for hadrons. Inside hadrons, they are tightly bound together due to color confinement. But under extreme conditions, they can break apart and form a new phase of strongly interacting matter. By analogy to the normal plasma, where electrons are stripped from the atoms, we call it the quark-gluon plasma. Now let us discuss the conditions necessary for formation of QGP. The deconfined state of quarks and gluons can only be achieved under extremely high energy densities and extremely high temperatures. The critical density beyond which matter gets transformed to QGP is 1 GeV per femtometer cube, and the corresponding critical temperature is about 200 MeV. Such hot and dense state of matter can only be produced by colliding nuclei of two heavy ions at ultra-relativistic speeds in particle accelerators, that is, at speeds close to the speed of light. This is a schematic view of the phase diagram of hadronic matter. Since quarks confined in hadrons go to a deconfined state in QGP, we can call it a confinement-deconfinement phase transition. It is not a phase transition in the thermodynamic sense, that is, the free energy or its derivatives need not have singularity at the transition point. Rather, it is a smooth crossover. The mechanism of deconfinement is provided by screening of the color charge, analogous to Mott transition from atomic physics. Now, the question may arise, why should we care about QGP? Just a few millionths of a second after the Big Bang, our universe was filled with a hot, dense soup made of all kinds of particles moving nearly at the speed of light. This mixture was dominated by quarks and gluons, and this state was none other than quark-gluon plasma. It is also believed that QGP exists at the core of neutron stars. So, a lot of these systems can be known by studying QGP in details. Now, let us talk about QGP and its stages of evolution. So there are four main stages of evolution. The first stage is pre-equilibrium. Here, initial partonic collisions produce a fireball. The fireball is initially not in equilibrium. Frequent collisions try to establish local equilibrium. The time taken to establish local equilibrium is known as thermalization time. The second step is thermalization, where the thermal pressure expands and cools the system. Also, thermal radiation is released. The third step is hadronization. In this step, the deconfined partons bind together to form new hadrons. The fourth and the final stage is freeze out. After hadronizing, the hadrons keep interacting for some time. When these interactions stop, the particle momenta are frozen and they stream out to the detectors. Now let us see what are the experiments being conducted for the study of QGP. Several experiments performed at the Superproton Synchrotron at CERN Geneva and Relativistic Heavy Ion Collider at Brookhaven National Laboratory, New York, have provided a significant evidence of the formation of this novel state of matter. As of now, both LHC and RIC have research groups studying QGP in details. LHC collides lead atoms head-on and operates at center of mass energy of 2.7 TeV, whereas Rig collides gold atoms. For Rig, center of mass energy is 200 GeV. We have observational access to only a single instance of the Big Bang, which created our universe. Rick and LHC have created a billion of little bangs, which have helped in the study of QGP. Now, let us look at how we can model QGP. A striking feature of QGP is that it behaves like a hydrodynamic fluid and hence can be modeled with relativistic fluid dynamics. The hydrodynamic features of QGP in heavy ion collisions are supported by the measurements of the anisotropic flow coefficients. The anisotropic flow coefficients Vn are defined by the following Fourier decomposition of the azimuthal particle distributions. In the given equation, E is the particle energy, P is the particle momentum, Pt is the transfer momentum, phi is the azimuthal angle, y is the rapidity, and psi is the reaction plane angle. Now, let us look at the electromagnetic probes used for studying QGP and obtaining unscathed information about its interiors. Photons and dileptons are better probes than hadrons because they are emitted from the whole volume of matter and interact only weakly with the other particles. Hadrons, on the contrary, interact strongly. Also, unlike hadrons, which are only emitted from the freeze-out surface, they have large mean free path and hence emitted from the entire volume of matter. Also, thermal photons act as thermometer for measuring the temperature of QGP. For more information about QGP, please head over to the given references. Thank you very much for listening.